All right, Algebra 2. So a while back, I sent you this table on Google Doc that you can make your own copy, and I just wanted to make your life easier so that you don't have to, get carpal tunnel writing this big old table. So you could just print it out and handwrite it in, or if you know how, you can make your own copy and type up the equation and plug in the values of n. So what this is basically saying is, okay, so you've got a table and you have a column n, you've got a column n plus 1 over n, and the third column is n plus 1 over n to the nth power. I figured it'd be easy to take this in 3 steps. Okay, so let's start easy. Let's start with, let's say n is equal to 1. So I plug in n plus 1 over n, where n is 1, so 1 plus 1 over 1. So that'd be 2 over 1, or 2, to the first power. Well, 2 to the first power is just 2. There's nothing too exciting about that. So that's kind of a letdown. So let's go one higher. Let's go with 2. So if n is 2, n plus 1 over n, specifically 2 plus 1 over 2. And so now I've got 2 plus 1 over 2, so that's 3 over 2. And remember that we're taking it to the nth power, so whatever that was is 2. So 3 halves, or 1.5. 1.5 squared is exactly 2.25. Okay, a little bit of a growth, nothing too exciting. So let's go on with the table. So let's say we've got n equals 3. 3 plus 1 over 3. Well, 3 plus 1 is 4 over 3. That'd be 4/3, so it'd be 1.3333333333. So if you put in the calculator parentheses 4 divided by 3, close the parentheses, and you take 3 plus 1 over 3, quantity to the third power. So 4/3 quantity to the third power, that would be approximately, I need a calculator for this. So let me try 4/3. Caret to third. I thought I wrote down the solution. So 4/3 would be 2.370370. So 370 repeating. So 2.370 repeating. Okay. Now I don't need this cover anymore. Okay, so then why don't I go a little bit higher? Specifically, n is equal to 10. So 10 plus 1 over 10. And then I'm going to take that to the 10th power. Well, remember that that is 11 tenths to the 10th power. And if I plug that into the calculator, I did this ahead of time. I thought I did this for n equals 3. But if I did 10 plus 1 over 10 to the 10th power, that'd be 2.59374, blah, 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 blah. Okay, well, why don't I go even higher? 100. 100 plus 1 over 100, so that's 101 Dalmatians over 100 to the 100th power, or 1.01 to the 100th power, if that makes life easier for your calculator, and you should get 2.704813, blah, 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 blah. All right, let's go even bigger. So I'm thinking that if these numbers get bigger and bigger, that the output should get bigger and bigger as well. But remember that if I do 1,001 divided by 1,000, if this is 1.1 to the 10th power, 1.01 to the 10th power, then this is 1.001, 1,001 rather. 1,001 divided by 1,000. Sorry about that, I feel really bad. 1,001 over 1,000 to the 1,000th power. Well, the point is, it's approximately 2.716923, and I'm scratching my head going, well, how come this number doesn't seem to get any bigger? Well, because as the n gets bigger and bigger, the scale factor, so in this case, as the inside of the argument, the scale factor gets smaller and smaller, and as you multiply by a smaller and smaller decimal repeated, the output starts to converge. And you learn a lot about this in actually in calculus too. So in college level calculus, or maybe even I'll say college level calculus, you'll learn about this, about, well, when does the growing stop, when does the decaying stop, and when does it meet to converge? So let's try a million. If n is 1 million, we play 1,000,001 over 1,000,000 to the millionth power. Try saying that 5 times fast. 1,000,001 divided by 1,000,000 to the 1,000,000th power. And that's going to be 2.718281, blah, 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 blah. The point of the matter is there's this idea in calculus called a limit. In other words, I put infinity there. We haven't talked about infinity in this course, but the idea is, what if we had the biggest number humanly possible? Okay, let me just get my red out of the way really quick. So let's say I've got 1,000,000 plus 1 over 1,000,000 to the millionth power. You would think that, okay, it's got 1,000,000 in it, so it's going to be really, really big. Well, you'll notice that as the number gets really, really big, that the scale factor gets really, really small, and it's repetitively multiplying it by itself, so it has to flatten out. This curve is going to flatten out at approximately 2.718. And there's something very special about this number, and it is called the number E. So E is known as Euler's constant, and I have this fond memory in college of there's this guy in my college class. He put his head rested on his fist, and he said, "It looks like Euler. Are you sure it's not Euler?" And the professor's like, "It's Euler." He's like, "I'm studying this for like 20, 30 years, and everybody in the world calls him Euler. I know it looks like Euler, but his name is Euler. The mathematician's name is Euler, and he's famous for the Euler's constant, among other things." So basically, it is the limit as n approaches infinity, as in, what is the intent behind n approaching the biggest number humanly possible? Well, E is literally 1,000,000 plus 1 over not a million, because there's 1,000,000 plus 1, 1,000,000 plus 2, and so on and so forth. So the biggest number humanly possible, infinity plus 1 over infinity to the infinity power, and you get 2.718. So if you're looking at your calculator, clear, how to access the E button? Well, you'll notice that in these blue keys over here, you'll access them by hitting second. I don't know how your calculator is at home, but it should be like an inverse button or a second button. But you should be able to hit second and division sign on these TI-84 calculators, and you activate the E button, which is 2.718 blah, 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 blah. But the idea is it's approximately 2.718 because it is infinity plus 1 over infinity to the infinity power. So what's so special about this? So here's where I make my confession and say I'm not that smart, but I can work the numbers out. So once again, I'm not an accountant, I'm not a physicist, I'm not a scientist, I just happen to be a really good public speaker who has a background with numbers. So in real life, you use the number E for radioactive decay, the relationship between alcohol consumption and the risk of a car accident. I looked that up on the internet. One of my favorites, actually, is Newton's law of cooling. So, before I get into all this, I want to make it clear that we are going to be talking about, not in this upcoming test, especially in this sort of shelter in place and the coronavirus being spread, and it's a scary time. We are going to talk about exponential growth and exponential decay, and I didn't time this specifically for the coronavirus. It just so happens that it's part of the Algebra 2 curriculum, and I need to talk about it. It's serious. It's serious because the math is going to show that we can do our best with mathematical models and logarithms to predict how serious these cases can grow. So anyway, so before I go into the coronavirus, I want to talk about the other real life applications of E. Radioactive decay, the relationship between alcohol consumption and the risk of a car accident. The difference one drink makes it doesn't increase it constantly. It increases it exponentially. It gets exponentially harder to keep your balance or drive a vehicle when you're impaired. But on something a little bit more positive, Isaac Newton's law of cooling, which I didn't know I was doing when I was in kindergarten and first grade and second grade, because my grandma used to make really, really hot food, not spicy, but like, fresh, meat, fresh vegetables, and so on and so forth. And I had a very sensitive mouth where, like, if it was too hot, I would go. So I would put my dinner in the fridge and I would put a microwave timer for like 90 seconds or 2 minutes, and hopefully it'd be like room temperature by the time I would eat it. But Newton's law of cooling, I wish I could go back in time and talk to my sixth grade, my 6-year-old, 7-year-old, 8-year-old, 9-year-old, 10-year-old self and say, you're a scientist because you took a hot dinner, put it in the fridge, and I wish I could show you the calculus math using the number E to predict what the temperature is going to be in 90 seconds, in 2 minutes, and so on and so forth. But most importantly, sorry about talking a lot about this, I just want to make sure that I'm not just teaching you mindless stuff. The most common thing that E is mentioned in is stocks, savings account, investments, and there's this thing called continuous compound interest. And I'll get to that really quick. Oh, sorry, I have time. So just to give a brief overview of that is, if you have a savings account, you have an annual growth. Well, annual means yearly. Well, I want to see my bank account grow if I put more money in it over the course of 4 times a year. Well, how about better than that? How about 12 times a year, 1 for each month? Or how about 1 for every week? How about 1 for every day? How about 1 for every second? And that's what E is it takes into consideration how much money does your bank account grow if you continue to invest money in there and it continues to grow. So please major in accounting if you want to know how continuous compound interest works. Sorry about the talking. Anyway, back to the math. So let's say I just practice with this. I just want to round to the nearest 3 decimal places by doing e to the second power. This is mostly just prep for your calculator work. So I take my button E, second and division sign, and I'm going to take that to the second power. And that's going to be 7.389. So 7.389. So what if I take e to the third power? E to the third power is 20.085. I'm going to round to the nearest third decimal place, so I'm going to make that 20.086. Okay, and finally, e to the fourth power. Let's say I multiply e times e times e times e. So e to the fourth power is going to be 54.598. Okay, so that was just practice to see if you can access the E button on your calculator. Okay, now look at your calculator. Let me pull this out of the side. Do you see the LN button on the calculator? Let me put it up so that the screen isn't so dusty. Let me see. Yeah, okay. So do you see the LN button right next to the logarithm? So if you zoom in on this log button, you'll notice that there's a button there's a button ln, and speaking of which, there's an e to the x button right there. So those are related. So log and ln are related. So we use the log button right over here to calculate base 10. So log base 10. So if I want to calculate log of 789, it's saying 10 to what power is 789? Well, apparently 10 to the 2.897 power is 789-ish. Okay, now if you see that the common log is log base 10, well, what does the ln button do? The ln button is known as the natural log. So if log is if log is base 10, natural log is base e. I'm going to let that sink in. Your calculator, as great as it is, understands base 10 and base e. Your calculator understands base 10 and base 2.718. So for example, if I do ln of 20, that is asking me, delete. So enter. So ln of 20 is 2.99573. So I just plugged in gibberish, but really what I'm asking myself when I do ln of 20 is log base e of 20. In other words, e to what power is 20? So if I plug in 20, sorry about that, e caret 2.99573. I'm going to get 19.99999. Yeah, exactly. Pretty darn close to 20. And that's awesome. So in fact, I want you to check your statements. So remember, if natural log is log base e, I want you to think to yourself, before you plug it into the calculator, well, e to what power is e? I'm thinking it's to the first. So let's calculate the natural log of e. Natural log of e is 1. Well, let me check with the natural log of e squared. 2. And finally, the natural log of e to the third. Yeah, it's pretty self-explanatory because it's asking me if this is base e, e to what power is e squared? E to what power is e to the third? It has no choice but to give me these unknown exponents. E to the first power is e to the second power is e squared, and e to the third power is e to the third power. Therefore, the natural log is a logarithm of base e. Okay? So one last thing before I let you guys go is I want to further verify, because I remember I said that there's this thing called the change of base theorem as to why we're doing this unit in the first place. It's not a magic trick. It literally is using the power factor rule. So remember, let's go back to the easiest problem that we can do. 2 to what power is 8? If I'm a human, which I am, last I checked, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. Aha! I can solve this as a human. I say 2 to the third power is 8 because of my little table. But I've been using the common log to solve this. As in, if I've got a variable as, sorry, if I've got an exponent that is a variable, what I can do is log both sides of the equation. So log of 2 to the x is equal to log of 8. And what that does is that makes this exponent fly to the front. Specifically, now I've got x log of 2 is equal to log of 8. Now it becomes a division problem. Sorry, a multiplication problem, which I can undo with division. I'm going to divide both sides of the equation by log of 2, getting me x isolated. So if I go to my calculator, clear. If I do log of 8 divided by log of 2, remember to close the parentheses, I'm going to get 3. Well, that makes me happy. I already knew that. Do you think I can do this problem with natural log? Well, let's find out. So suppose that natural log of 2 to the x power, and I use the same properties of logs by making the power factor rule, slide that exponent to the front. X ln of 2 is equal to ln of 8. Now I've got x ln of 2 is equal to ln of 8, but I want to solve for x. So what I can do is divide both sides of the equation by ln of 2. That cancels out, so I'm using the properties of logs to say the natural log of 8 divided by the natural log of 2. Do you think I'm going to get the same result? I still get the same result, 3. There are 3 ways now that we have determined how to solve this problem. So what am I here to tell you? If I solve this using the common log, let's go with one more example just for the heck of it. 7 to the x power is equal to 49. You and I both know the answer is 2. So if I do log both sides, I get x log of 7 is equal to log of 49. And now what I can do is divide both sides of the equation by log of 7. Getting me x is equal to 2. If I plug in log of 49 divided by log of 7 in the calculator, let's see if this happens again. X ln of 7 is equal to ln of 49. And now I'm going to verify my result by doing it this way. So let's check my work. If I do the natural log of 49, close the parentheses, divided by the natural log of 7. Naturally, I get 2. So we've proven with both ways, using the common log and using the natural log, that we will get x equals 2 for 7 to the what power is 49. So why am I saying this? Why am I ending it like this? Remember that the goal of a logarithm is to solve for an unknown exponent. And according to the change of base theorem, your calculator doesn't understand base 2 or base 7, but rather only base 10, the common log, and base e, the natural log. You can apply the common log or the natural log. It does not matter, because you've tricked the calculator into understanding it into a base that it understands. Exactly. That's what I'm really excited about this unit. And the next video, we're going to be doing log expansions, and those big 3 rules. They're going to come back. Have a great day.